people. Questions about homework 1? Everybody is happy? Homework 1? Okay, very cool. So we are working our way toward homework 2, which is similar to last year's, not identical to homework 2. Maybe. What did we have in homework 2? We had things like 2 billboards. You see right here. So there are 2 billboards. Both carry the same image. They are not coplanar. Remember, I specified the billboard by specifying 3 vertices out of the rectangle, but I don't necessarily say that they all have the same distance from the viewer, or that one is vertically above the other. There are just 3 points floating in the plane, and then you know that the 4th one can be obtained from the other 3 by, we had this vector calculation. Right? Repeat it, that if I give you the lower left, upper left, and upper right, then the last one, the lower right. And I'll always use this abbreviation. Lower right that is not given to you is lower left plus location,
plus upper right minus upper left.
That's it. And that's give you the coordinates. And of course, you're doing it in x, y, 0, x, y, z, w, if you're working in homogeneous. And then you have the 4 coordinates. Think about the points, or think about this as a vector, this vector that goes from this point to this point. And that's an example of output of homework 2. You have 2 billboards. They happen to have the same image on them. And I created, and one thing that will be different in your class homework is that you'll have camera position. Camera position meaning that the angle, where x, y, z is the camera, and the up vector. And you'll have it twice for initial and ending, and I'll ask you to generate 10 images or so in between with some linear interpolation of these vectors. So here I'm just changing the up vector without changing camera, which creates the idea that it all rotation, because the up vector is just once you change the up camera, the up vector you are changing, well, W stays the same, but U and V rotated accordingly. So that's how you're creating this one. So you have this creature in homework 2, and you have what is this? Yeah, I don't remember which. And you have, for example, this one billboard. You have spheres in homework 2. You do have spheres. You don't have mirrors of spheres. So this sphere in the middle with that is a mirror. You don't have to worry about it. You'll have diffuse shading. About specular, I don't know. We'll see how much we are covering today, and that we'll decide about the specular with shading. The specular are these white things over here, and we'll decide accordingly if we want to have them in this homework or not. And it will, and you assume that each ray here, what are you doing with each ray? Each ray, you're generating from the eye via a pixel until you hit an object. If this object is opaque, we return its color. If it's a billboard, for billboard you don't care about shading. If it's a sphere, then you want to know what is where do you hit the sphere, what's the normal to the sphere where you hit it, and does it see the sun? There is a single sun, and you want to shoot one ray to the sun and see if this ray hits any object on its way to the sun, or does the sun illuminate it, and then you know about the diffuse reflection, of course. If you want to also have specular reflection, specular shading, then you also need to ask what is this angle with respect to the viewer, which introduce yet another level. But the depth of the recursion is either one way or two ways to ask what's a point that I hit, see or doesn't see the sun. You don't have more depth of the recursion that happens if you have mirrors or want to ask for surfaces how much this surface is illuminated, and the same surface how much this surface shed light, cast light on other surfaces. That requires more depth of way to way to way to way. That's all waiting for us. And it will run slowly, expected. Especially on your laptop, especially there is no GPU involved here yet, waiting for us for homework 3. Yeah, and depending on the resolution, you have to, I strongly recommend, start when the billboard as well as the image resolution are very low, see that what you're getting makes any sense, and slowly up the resolution of them, because it will run slowly, and it's less frustrated if it runs 30 seconds and it's not what you wanted, rather than one much more, and then it's not what you wanted. So see if it makes sense when it's 10 by 10 images, and then work up. Okay, last time we talked about translation of the image plane into canonical representation, had it U, V, W. We specified the formula Pij where each candidate pixel is after we created U, W, and V. Where is Pij? That help us shoot a ray through Pij, and the location of the Ij is given by this formula. And if you want, it's -1 if you start from 0. If you start from 1 till number of pixels, you don't need to the -1 over here. We leave it up to you. Any questions about everything we discussed last class? Cool. Yeah. UVW, we talked about rotation matrix way back. If I have UVW and I want to see it in XYZ, I want a translation matrix. Here it is if I need it. And maybe I'll show you another way to debug your program using projection, perspective projection matrix. Maybe we'll have time for it today, otherwise we can also wait. Original ray tracing, you know, here is the eye, one of the rays that I hit the sphere. I know that I hit the sphere. I want to ask how much light is illuminated from the sphere, and it depends first, is this in the shadow or not, or is a source of light illuminated. I want to know what is the reflectivity in RGB of this sphere. If it's blue, then it's a lot of reflectivities in the B channel and much less in green and red. And of course, I want to know if the light is white light or blue light or green light, depending for all of it. Okay, so compute the view ray, intersect the ray with the scene, compute illumination, which is exactly where you are either sending a ray from here to the sun or a ray from the sun to this point, and asking, is there something that blocks my view or not? And eventually I know what is a color at this point, and that's the color that I assign to this particular pixel. I think I said it many, many, many times. Okay, for each pixel, compute what is a viewing ray based on Pij, based on the location of the eye, what is Pij. Don't forget the whole order of the things, right? We started from having the look at and the up vector, which helps us generate the W vector, which helps us generate the U and V vectors. And then we use the angle to compute the distance to the image plane. And then UV plus the number of rows and columns help us generating the factories, the pixels, and now I shoot a ray through each one of these pixels. It was a very ordered part, and I want the code that will tell me that it intersects for the eye XYZ direction, a vector. Maybe I also want to give you what is a minimum distance and the maximum distance. Again, not very important for our application to have the max and min. Very important when we want to use GPU, because the matrix, the projection matrix needs to know here is a maximum and the minimum distance, and it cannot be 0 or infinity for either. So not very critical at this point. And what this code returns for me is which objects did I hit with the smallest time, presuming that this object is not a transparent pixel. Talk about it, pixel have RGB. Alpha is 0, your ray just happily continue through it. Okay, an intersection with many types of shapes. You'll have the reader for the JSON. And the JSON file, the reader will produce an array where each object in this array is one array for spheres and one array for billboards. And then you can ask what is the lower left coordinate of the fifth billboard in my array of access. The array ones after the other, and you don't need to and it all happens automatically in the sense that the fields, the attributes that we have for the billboards in the JSON files will appear in your program, and you can read what's their values. That is as humanly kind as a JSON file can be. And JSON files, without talking a lot about it, I showed you an example of the JSON files that we're giving. A few parameters at the beginning, eye, location, direction, etc. And then in XLS format one, you don't need to really read the JSON files directly. And obviously you don't need to edit it manually. Okay, for each pixel, let the eye directions, giving the camera ray, let the hit surface be undefined, start with Tmin and Tmax, and now for each surface, check intersection point. Does it happens in this for the eye and direction, Tmin minimum T, maximum T, and did I improve the hit or not? Just remind you, you might get that you hit billboards, but it happens in negative T. Just tells you, I don't care about it. It's behind the camera. My equation that tells me intersection points of billboard and array or sphere and array doesn't care that the T needs to be positive. You just get negative T, you just don't affect anything about it. And once you hit the array, you are updating the color based on the color of the objects that you hit, plus whatever shading effects that we want to have. And I still didn't tell you exactly what I mean by shading effects. So let's talk about the illumination. For each pixel, compute the viewing ray as we had before. And now, in addition, I want to compute what is the illumination at the sphere where my ray hits, right? I want to know that this point of the sphere, this point of the sphere is darker than this point of the sphere. Here I still don't feel the specular shadings that you see right here, but you see that this is much darker than this. Why? Because the normal over here is partially pointing toward the sun. Some direction to the sun is somewhere here. And on the equator, I'm far away from the sun, orthogonal to the sun, completely. And below the sphere, I barely see anything, but I do see things in the dark side of the sphere. How come? Because we'll have ambient light, and ambient light doesn't care about directions. A promo for something that we'll discuss later in the course. There is a beautiful technique from video games design that calls ambient shadows, which is self-contradicting, ingenious branding name by itself, because shadows and ambient contradict each other, but you are still doing something with both of them, and it creates great effects, but not in this homework. Yeah.
So like, as if these are like 3D objects, so when you like calculate like shading like that, do you just calculate from the pixels that like the viewer see, or do you calculate of the entire object itself? So like that is a 3D ball, right? So like this is the faces the viewer sees. So do you just calculate the pixels from there?
So I use ray tracing, but here meaning that I generated the image plane, and now each ray independently through this pixel and through the eye. I shoot a ray, and I see this ray continues until it hits the surface. And the surface is white. I see the color of the surfaces, and if I just need, in the debugging stage, for example, to care for ambient light, whatever the color here is the color that I'll assign to this point. If you want to use diffuse shading as well, then you ask what is the normal right here. The normal right here points this direction. Projector is right here, it's pretty much in the same direction. I just do the dot product and look at this number, and that tells me that most of the light is here, so it's highly intense. On the other hand, so I need to shoot a ray from this point also to the projector, to the sun, because had something block this way, then it will be only ambient light that will be here. Did I answer? So we are mimicking with a single core CPU ray tracing, and that is as opposed to go for each object and project it onto the plane. Maybe I'll suggest it as a debugging way of how to project a billboard, how to compute at which coordinate the corner of the billboard appears on the camera, but I don't think that I'll have time for it today. But it's a homography matrix that connects nicely between them. But for this homework, once I decided about array, I don't care about other array, I don't care about the resolution of the image. I pick where this ray hit, pick the object. If this object is a sphere, I'll ask what is the color of the sphere. If this sphere is a billboard, then using the alpha beta trick that I showed you last meeting, I find the pixel of the billboard at this very point, and that's what I retrieve. For billboard, I don't care about shading. For spheres, I'll also need to know what is the normal to the sphere and whether it sees the light. Okay. So here are two spheres that you see in this picture. These are two three-dimensional spheres that you see I shoot away, and this ray hits the green sphere, so I'll return that that's green. This array over here hits a blue sphere, return that it's blue, and that's the image that I'm getting. That's how it should look like if all you are using is ambient light. And it's probably a sphere, it can be other shapes that have the same silhouette. Maybe it's a cylinder, maybe it's a cylinder, it might be a cylinder that still looks like this. That's very, very boring way to look at the sphere and give you very little information about the 3D structure. So that's if we only use ambient light. So what is ambient light? Every object has 3 coefficients, each pixel, the coefficient per ambient light, the R, G, and B, we'll talk about it more. The light itself has its own coefficient. If it's white, then it's 100% blue, 100% green, 100% red. And if it's blue objects times white light, what I'm basically reflecting is just mostly the blue light. And that's a color. And I don't care at all what's a normal at this point and what the direction of the light. The light doesn't have a direction. It has its color, more blue, more green, more red, but it doesn't have any particular direction that it comes from. So that was a very boring way to look at the sphere, very boring way to look at this shape. Very classical example. That there is this plastic, what is this, union of 5 spheres, more or less, that with ambient light, that's how it looks like, completely flat. It's blue, as it looks right here, and it looks completely flat. And now I notice that actually, because it has 3D structure, there are normals to this sphere, and these normals might point towards the light or away from the light, suggesting that some regions are brighter than the other, reflects more intensity than the other. And that's immediately discovered for us where is the source / sources of the light, and how are the normals with direction to these surfaces, to the sources of light. Probably the normals are here and here and here pointing towards the light and the dark side of the object. And already you get pretty good idea about the 3D structure of it. That's using only diffuse shading. We'll talk about it more. Diffuse shading is nothing but direction to the light, normal of the surface, multiply these two because you want the cosine of the angle in between, and this cosine is a coefficient that dims or allows all the light to be reflected. If the cosine is closer to 0, the normal is there, but the direction to the light over here, then I'm pretty much in the dark. And now you realize that maybe this object is shiny, like covered by some lac, some shiny paint, and there are also the specular spots over here. And these are the specular shading that is added on top of it. And now it looks way, way more alive. The 3D structure, it looks much more alive. And what's the big difference between diffuse and specular is that to know what is a specular shading, I also need to know from which direction the viewer look at this shape. Diffuse doesn't care one bit where is the viewer. Specular cares very much where is the light and where is the viewer. Diffuse cares only about where is the light, but not where is the viewer. In other words, if now I'm moving, the viewer is moving, the specular spots, these white spots over here, will move as well. They'll adjust to the new location of the viewer. The diffuse shading over here will stay the same. these are the three main shading effects that we'll talk about. If we'll have time, we'll talk about specular shading a bit more because it goes much further beyond what specular shading, sometimes called Phong shading, which is wrong, but it's still fine what you're discussing about. Phong will we'll mention Phong a few times in this course as always with respect to shading, but it will respect to different things. Phong will help us when we talk about triangulated mesh, how we are looking for something that is polygonal and make it look more smooth. That would be one usage of Phong. And Phong formula, or Phong approximation, here is a full sentence. The Phong approximation for specular shading will give us a strange formula that doesn't aim at all to be realistic, doesn't aim at all to capture the physics that happens out of it, but the Phong approximation makes the specular shading looks realistic. Okay, that's the only justification that we will have to it. It looks good and it looks like the Phong, the specular shading are in the right place. But it's fine for such isotropic surface that is fine for plastic, but you'll expect metal surface to look very different, not only for the specular, but also because the direction at which you walked on this metal surface should affect something else. It looks very smooth, and beyond the Phong shading itself, there are tricks that tries to capture more directionality of the surface itself, which is quite useful if you want to use to mimic metal surfaces in particular. Yes, sir.
Assuming that the material is isotropic, does the specular shading depend on the absolute position of the viewer and the source, or would it only depend on their relative separation angle?
The Phong shading, that is a first thing that you'll find in every textbook, depends on you're looking at the angle. We'll talk about it much more. Looking at the viewer, and here is a direction of the light, and the way to understand Phong shading, we'll talk about it more, is first imagine that this surface behaves like a perfect mirror. So this angle alpha equals to the reflected angle alpha, exactly. Imagine that is exact mirror, so think about making the surface from exact mirror. Where do you see, and you have a few point source of light, where do you see the reflection of the light on the surface? Exactly when the incoming angle equal to the outgoing angle. Alpha equals alpha. Phong shading says, hey, this, even though it's point source of light, the spot over there is a bit wider. Why is this a bit wider? Because, and I think that that's answer your question, even if I'm not exactly at alpha, but I'm in angle of alpha plus minus some theta over here, I still see the reflection of the light right here. Plus minus theta. How much away from theta and how to reduce it when theta is becoming larger, that's depending on the material. It will be a coefficient called the Phong coefficient that tells you how center you are, how close to a perfect mirror, or how wider it is, closer to a smooth plastic it is. But that would be the Phong with its own limitation. Now, you can go the full direction, since you ask, into the BRDF, bidirectional reflectivity distribution function, that takes exactly the direction of the light with respect to the surface, exactly the location of the user, and now try to mimic it in a better way, more realistic way, and less pleasant to implement, if you wish. But depending on the material, you might want to go either to the Phong interpolation as a minimum, BRDF, and maybe we'll cover things in between. So for the BRDF function, you need to have 4 parameters, that is, which direction is the light coming to the surface, which direction is the viewer comes to the surface, that is, it needs to take 4 parameters. Phong interpolation just ask what is the theta that I still want the lights to be existing. So I cared about only one direction. Okay. Notations, and back to a much slower progress in the course. L will be the direction of the light, N will always be the normal, vector that is normal and going outside from the surface, V the direction to the viewer. Done. Okay. So we'll try to be consistent with these notations. I should have also assumed that if I have one source of light and objects are further away from the source of light, they should be illuminated less. If I look at the physics around it, I would think that 100 photons are sent every second from the source of light, and this 100 of photon kind of emerging, moving its speed of light further and further, and the intensity is just how many photons falls in every square inch. And if you think about the area of this sphere, where my photons are in 2D, these 10 photons, this cluster of 10 photons, the area of the sphere increasing as an R square, right? It's not the volume, which is R cube. It's not the perimeter, which is just R. It's the surface area of the sphere, which increasing as a function of R squared times a constant. So the intensity should decrease as a function of R squared. Great, that's very realistic. It doesn't work in most video games, at least that's what the textbook claims. Why? Because R squared just decreases too fast. And then objects that are not very close to the lamp just are in the dark. So what should you do instead? Either do something that decreases linearly or even sublinearly, or don't do anything at all. That's the advice that I usually have, assuming that the ambient light is strong enough that you don't want to do it unless you want to create something with special dramatic effect. That's a different story. But if you think about normal interactive computer game where the player move inside the scene, don't ignore the distance to the light. Just usually doesn't affect. Or at least, and if you do want to use the distance, don't ignore the physics behind it and just decrease it as a linear function, not as a quadratic function. Quadratic function will just get that if it decreases R squared, then the intensity would be 1 proportional to 1 over R squared, very close to 0, very far, very fast away from the distance. Okay, intensity, I for intensity, we'll see it in other slides, divided by R squared. That's what the physics tells you. To be precise, shading and shadow are very different things. You will have to implement both in homework 2. That is shadow, meaning just you have the ambient light that illuminates them. That the shadow and shading are Phong specular shading, how does the location of the viewer allocate direction to the light affect how well it is. That is, shading is something at which only a small patch of the object affects the shading and the direction to the light and maybe direction to the viewer. That's for shading. Shadow doesn't care about the normal to the surface, but depends on either any object that blocks the lights to the surface. Okay, so we will cover diffuse and probably specular shading today. Talk about the ambient coefficient or albedo coefficient. Every material has observed some of the energies that falls on it and reflects some other parts, even independent of the colors. Just as far as energy is concerned, then the data that I showed and that I bring say that if you are looking at fresh snow, almost all the energy is reflected, and it's white, meaning that all the RGB, all the that it's close to 90% for all the frequencies that falls on snow. While if you go to, where is this, coal somewhere, soil and do I have dark coal, lost it, coal, soil and heavy coal reflects very little energy. And just notation, albedo doesn't care about the color anymore. Usually it will be a vector that refers to the RGB. Okay, so when you are playing with OpenGL and you describe a surface or a vertex of the surface, it will give you the option to opt to default, not to specify some of the parameters, but you can specify up to 3 parameters that refers to the shading. And there are 3 parameters that refers to the ambient, how well it reflects ambient light, how well it reflects specular light, and how well it reflects diffuse light. For each one coefficient for R, 1 for G, 1 for B. Okay, so when we talked about the diffuse, D here stands for the diffuse. That will be the only one that you start really, you notice the shading, of course. The ambient, how much red light is reflected from the surface, independent of direction, all direction, omnidirectional. How much red light should be reflected? It's a coefficient for the diffuse times how much red do I have in the light. Similarly for the green coefficient, again, coefficient between 0 and 1. It's not a lamp, it doesn't generate light. It just reflects percentage of the green light that falls on it. And this percentage would be exactly what this coefficient is. And now I look at the red, at the green, at the light that comes, how much of the green do I have in the light that comes, and that's how much is reflected. And similarly for the blue, which is just a very convoluted way to say, hey, if it's a blue object, then K of blue, it reflects most of the blue light that comes, while the red and green are barely or not at all reflected. Just convoluted way to say that by playing with these 3 coefficients, you are just determining what the color of this object. And OpenGL, other similar packages, lets you specify 3 different sets of variables, 1 for diffuse, 1 for ambient, and 1 for specular shading, if you want. Okay, not in the homework, so I don't refer to it. Too much, you'll have, for the spheres, you'll have 3 coefficients, each sphere in the homework, and you're referring to them as a coefficient. For the RGB, the same coefficient, but also for diffuse, for the specular, and for ambient light, the same thing. Okay, so now, introduce to you this nuance and also say that we are not going to explore these nuances. And here is my flashlight. I want to explain how diffuse effect works. I think that all of you have seen it probably at childcare or some early stage, but let's talk about it. Flashlight, every second sends 3 photons coming up from the flashlight. They are all moving in parallel. It's almost a laser-like flashlight, and they all fall on this door. And what is the intensity of the door? What is the intensity of the reflected light from the door? Well, it's 3 photons, say, per square inch. 3 photons per square inch. That will be our baseline our baseline intensity. But that's happen when the door is orthogonal to the direction of the light. The door that I'm going to open, right now is orthogonal to the direction of the light, or the normal to the door points to the direction of the light. Actually, they are exactly collinear, but directed opposed to each other. So 3 photons per square inch. And now, do I have the animation? I don't have that. And now I open the door, partially. I power the door that pointed towards the light, it's partially open or partially closed. So the normal to the door is not pointing towards the direction of the light anymore. And I'm asking how should it affect the intensity of the light reflected from the door? And the answer is very simple. It's very, very basic physics. You don't need any optical knowledge out of it. You're just asking the same 3 photons that falls on 1 inch now falls on the more of the door. The area exposed to the flashlight is larger. How much is this larger? What is the ratio of the length or the area between E and F? Answer. Let's look at the angle in between. And now the angle is not, or the area is not 1 inch that the 3 photons are falling on, but it's an area of 1 inch divided by cosine alpha. Okay. This length divided by this length is cosine alpha. Or in other words, this length, F, equals E times cosine alpha. Make sense? Well, so the intensity should decrease by a factor of 1 over cosine alpha. Reflected intensity is what would have been if I would point directly to the light, divided by cosine alpha. But I don't like cosine alpha. Cosine is a slow operation and I don't really need it. What is cosine alpha? I'll keep one vector that goes to the light, one vector that is a normal, and this vector dot product this vector, assuming that the length of this is unit and the length of this is unit, this times this dot product is cosine alpha. Cosine of 2 units. Vector is just a dot product of these 2 vectors. So what should be the intensity of the door when it's open? It's the original intensity divided by 1 over cosine alpha. That is 1 over cosine alpha leaves you with just cosine alpha. So it's just the original intensity times cosine alpha, which turns out to be nothing but yada, yada, yada. The original intensity times L, vector to the light, dot product n, the normal to the door. And hey, what is this number over here, KD? that the coefficient that refers to the color of the door, how much of the intensity. The door reflects, it's a red door, so K of red will be large and K of blue and green will be smaller.
Oh, so it's kind of like wavelength. Or like, it's kind of like in physics, like the light wavelength of how much it absorbs light.
Yeah, we're giving it as the maximum will be 1. So
like
the
white
observer
is
is
one,
1,
black is 0.
1 minus KD is how much is it observed.
So like white will be 1, black will be 0, and in between is like the color.
If it's strict red, then it will be 1, 0, 0, yeah.
Yeah.
So n is the vector normal to the door?
N is a vector normal to the door, yeah.
It's right there, I guess.
So we talked about the ray R that goes from the eye to via Kj, one of these factories of pixels that take place, and it hits the sphere at a point Q. And we studied last meeting how do I calculate Q, with solving this numerical equation, finding at which time the heating takes place, and then I can also specify the point where the heating, the first heating takes place, because this way it might hit the sphere once again when it exits. And now, here is a light, source of light, the sun. And I want to know for the viewer how illuminated Q is. How illuminated Q is, which requires me to know what is the vector n. How do I find the vector n? I want to what will be the illumination at Q will be how much light coming from the sun times the color of the sphere, blue in this case, times this normal of the vector L. It's a normal vector, I just do it long. The vector L that goes into the light, into the sun, dot product N, which is a normal to the sphere at this place. That's how you created the sphere, how I created the spheres over here and here. But we talked about finding the intersection points. We didn't speak about how do I calculate the normal. We just want to hear from other. How do I compute the normal to the sphere display? The direction to the light, once I found, let's retrieve. I have the I have D, the direction. I look at I plus T times vector D, solved the equation of C minus, solve the equation X, Y, Z minus C square equals R squared, X, Y, Z minus the C center. Well, the center, I solve this equation. All the points X, Y, Z that satisfies it are on the sphere, not to be confused with the ball. If I want to see the whole ball, it should be smaller or equal than R squared. If it's exactly R squared, it's the skin of the ball. It's a sphere. I solve this equation. I ask for which T, when I put X, Y, Z here, for which T this will be equals to this, give me the time of the heating. Now when I have T0, I look at the point I plus T0D, calling this point Q. That's a heating point. And now to know what's the illumination at the heating point, I need to know the direction of the light. the direction of the light, L would be what? Light minus Q. Light minus Q. Light minus Q is the direction to the light, normalized by light minus Q, of course, because I like it to be a normal vector. But I need a normal. Help? Somebody else?
But that is the normal. The vector from, or Q minus C would be the, right, if X, Y, Z is the
Q
points
minus C.
Yeah.
Q minus C is a vector that goes from C into Q. That's, if I continue this vector, it is becoming N. Well, except that the length might be not the length that I want, so it's divided by Q minus C. And then it's a dot vector. And then what is the intensity over here? The intensity will be the incoming intensity, I, times KD. Remember, KD is a vector. It's the reflection in green, the reflection in blue, the reflection in red. It's 3 parameters, times, and that's the important thing, N dot product L. That's a cosine that is relevant for us, right? That would mean that for this direction of the light, if this point Q will be completely dark, because the cosine is 90, and this direction that is almost point directly into the light, that the normal points directly into the light will be have the maximum illumination.
You said computationally speaking, it's good to avoid the cosines, but I'm just thinking about practically finding all the, like normalizing all the vectors is a lot of square root operations, which is because you have to square everything and then take the square root to normalize.
White.
So when is it faster to just take a cosine? Or
I think that you have to do it all the time, otherwise, if I have a small sphere and a large sphere, one will be illuminated differently than the other because the L vector will be different. So,
yeah, but just in terms of, you could get to the same answer by normalizing them, because then when you take the dot product, you get the cosine, versus just calculating
for this
the
sphere,
angle.
you're absolutely right. But
Yeah.
if next to it I have a sphere which is much smaller, but the same geometry, then the length of this vector will be different, even though they both point to the same direction.
Yeah.
Which will affect this dot product. And the dot, and I want this number to be between 0 and 1, which if I don't normalize it, it can be anything it wants. So if this is more than 1, then this dot product might mean that there is more light reflected than light coming. So I understand, I never thought about it, but yes, it would have been nice to avoid the normalization. I don't know of any tricks.
No, not avoiding it, but when does it would it ever make sense to calculate the angle rather than normalizing the dot products? Because we're trying to get the cosine theta. So would it ever make more sense to calculate the angle instead of normalizing the vectors and doing a dot product?
I doubt it. Once it's, but let's take a step back. My training is in computational geometry with algorithm and proofs, and as the many areas that I worked in, I know I was Cavanagh as a scavenger, as a researcher. I picked an area, studied a bit, worked with people that knew about it, find interesting problem, and sometimes was able to publish in venues that was related. As such, I had a few papers in specific problems in graphics. I would never ever, I'm very proud computational geometers. I am not expert in graphics. I know the bits that I know and bits that I read more, and bits that I published that was epsilon that. So take what I'm saying with a grain of salt. Dot product is A, something that is just multiplication of three numbers and summation, and B, that the hardware optimized to it. All these dot products, nothing of it in real life are done in software. Your GPUs, what you generally do is tell your, and we'll do it in this course. I'll tell you what are all the parameters at this vertex, and at this vertex, colors, shading, etc. And then for every pixels inside this triangle, the normal, including the approximation to the normal, I'll actually have to approximate the direction of the normal itself. Even though triangle is flat, Phong approximation would want me to actually pretend that the normals change as I move along this triangle A and B. Even for different points, I need to do this dot product, and it's all done in hardware. So, and computing cosine directly, the only thing I know is Taylor expansion, which I need to know first what is theta directly.
That's what I'm saying.
So
that's my question. Is does it ever make more sense to calculate theta directly rather than doing all of the square roots to normalize the vectors?
If I create the scene by controlling theta as a user parameter, maybe.
Okay.
If it's geometric scene plus geometric parameters, like in homework 2, you never if it's not part of the input, tries to avoid it. Okay. I think that the only case that was really unavoidable to use trigonometric function was when we computed the distance from the image plane to from the camera to the image plane, and then D was, remember, 1 over tangent of this beta, which is alpha, the overall angle, over 2, and then I couldn't avoid using the tangent. But that was because alpha was given as a parameter to the user, what I want the camera view angle to be. If I would give it as a force term, which is another way, just to specify the coordinate of, 4 squares that is the closest 4 squares, 4 vertices that are the closest, 4 that are the furthest, I'm not even sure about this part. So far, just to summarize, so far the only case that I needed trigonometric function directly was to compute the distance to the image plane. Every other place it was only vector multiplications, dot product. Very good questions. So everybody is good with the diffuse part, how to create a diffuse shading on the sphere. Once again, you have the sphere, you have the eye. This presumably start your homework to in this case. Here is the eye, you created the image plane. On the image plane, you created the points P1, P2, P3. Each point Pi defines a ray from the eye through Pi to this point. Find the intersection point of the ray with the sphere. At the intersection point, compute the normal, compute n, following this algorithm. Check if you see the light and if you see the light. Then do the cross product the dot product to see the effect of the shadow. So that's what needs to happen in order to make this side of the sphere darker than the top side of the sphere. Again, not to mention the white spots over there, that's a specular effect, that's the other one. Okay, once again, the intensity of the diffused in this term here for RGB, each one of the values, is how much the diffuse coefficient, how much it reflects red or green or white, times the intensity, times N times L. But now, what's going on? Why do I need this maximum between 0 and this number? Well, because of what happened for the viewer that sees this point. And now here is a normal, and this is the direction of the light. And now when I multiply, that's the direction to the light. Doesn't care about it, it's in the sphere, that's a normal. And when I multiply both of them, it's negative value. So you'll either have a negative number right here, or if you have a few sources of light, one of them will reduce the value of other ones that's coming in diffuse light. And you don't want either. You want you cared for the diffuse only for the parts that are actually have a chance to be illuminated by the light. If this number is negative, then actually you're saying it's not a part of the sphere that is illuminated by the light, so it's only ambient light, if ambient shading if I have any, or 0 if I don't have ambient, and then it should be dark. And that's the effect. You see clearly what is the direction of the single sphere. You see exactly the equator, the dark side of the sphere on the other hand, and you see the gradient, exactly how it changes along the sphere. Okay, and you can, keeping the ambient the same, you can make this effect of equator dark and the pole, North Pole illuminated. You can make it more dramatic or less dramatic depending on which value you keep to KD versus the ambient light. You see the sphere because of mostly the ambient light out there. And I love this slide. You know the answer already?
Oh, no, sorry, that was another question. But, so the diffuse lighting will never make a point darker than ambient, right?
Correct. At the end, we'll have a formula that says I sum up ambient plus diffuse, each one independently. If I have two sources of light, I just sum up the intensity. It's stretching the physics, but it's good enough. If I have a few sources of light or source of light that is flat and not point source of light, I'll just sum up or integrate the overall contribution, plus again sum up the specular effect. And then all I care for is that I don't get overflow, making sure that the overall contribution is not more than what I can display. Good. So I want eventually something between 0 and 1 for the intensity of the light. Help. Source of light, pole highly illuminated, equator barely illuminated. There is an equator somewhere. The dark side of the moon is clear, but what is the side that points to the sun? It's slightly more illuminated, but it's not dramatic. So yeah, need explanation. What happened to my physics over here? Let's turn off the lights. The whole theory about the normal that towards the equator it should look darker than towards the pole. Nothing of it happens on the sun, on the moon. Yeah, that's darker, and that's maybe the equator, similar, a bit darker than this, but not nearly what you see over here.
Well, isn't that basically the moon cycle though? Like in a moon cycle, we do see the crusher shading.
Second?
Like in a moon cycle, that's basically crusher
Moon.
shading. If like you only see like it's a half moon, that's basically what crusher
Yeah,
shading
yeah. Here it's when I do say the full moon. Yeah, it's.
is. Yeah, so we can
That's
see it,
that.
which is-
Yeah, that's not the effect. You sometimes see portion of the moon, but once you see, you don't see such dramatic effect as the dark side of the moon is the dark side of the moon, but the illuminated side is almost uniformly illuminated. So how come?
Well, same reason we can't fake the moon landings, because the sun is so far away and so big compared to the moon that all of the light's coming in planar versus a point source that's like a finite.
I understand it might contribute. It's not what the book said, but so it's much beyond. But it might help, but I don't think that that's a main reason. But it definitely can contribute, and I didn't think of it. So.
Is it because the sunlight, the light from the sun, it like covers a large enough area that like we can just, but like it basically illuminates the entire side.
It's left off there.
It's not a reflection of what you see is what you have. There is no more effect that we didn't discuss in class. You need to explain it, and using only what we studied today. There is no other effect. The sun, for this purpose, is a point source of light. That's all within what we discussed today.
The relative distance, though, that the attenuation as you move across the moon is going to be really small compared to the large distance between the objects.
That's true, but that would have been two other. There is a gap of attenuation, but the darkness that we see over here is not a function of the distance. It's a function of the normals to the light.
Is it because of the surface of the moon? It's not like smooth, so it's just a diffuse. So like.
What's a normal at this point?
Yeah.
What is a normal here versus a normal here? Normal
Yeah,
here,
it's not
I'm pretty sure at which direction this normal is, and it's definitely a large angle with respect to the light. Normal here is close to 90 degrees compared to here. This is not smooth. The moon would have looked, had the moon be perfectly smooth, that's the effect that you would have seen. Every point that I'll pick have enough normals to each direction, including the direction that points directly toward the sun, including direction. What we'll study is that one of the coolest way to create texture that looks like this would be exactly to keep the surface completely smooth, but make the shading effect believe that some points here have normal differently. That looks very awkward sentence. When I ask for a ray, where does it hit the moon? The answer would be, the moon is completely sphere, each point is equally likely. When I ask how much shading do I generate, at this point I will use texture, but not the texture as a color, but the texture as a way of think that a normal where I hit is not pointing according to the exact sphere, but as some displacement of this normal, either by changing display or not. It's one of the coolest ways in computer graphics. It means that when I compute ray intersections, where it is in graphics, what is the object. It's a very simple surface, it has very simple complexity. A ray that hits out there, I don't care at all that it's, if it's rigid or surface or smooth. A ray will hit according to the formulas that we just saw over here. When I cared about the shading, how much light do I give to this point? At this moment, I'll pretend, using the texture, that the normal is not this normal that I computed, but something that is a normal that I computed, plus some displacement that I pull up from a texture image. And that's how I will take perfectly smooth surfaces and make them look like they have ridges inside it. And sometimes that will not be enough. That's called the normal map. And sometimes I'll actually need, if I'm very close to the surface, to actually make some ray tracing, very, very simple ray tracing per point according to the surface, and that's called displacement map. Google for both and look for examples. It's extremely cool and allows us to have very complicated surfaces and still very cute, very quick calculation of what occludes what. What is the closest to the viewer, despite them being very complicated 3D structures. And that would be one of the examples that the term texture in this course, or in computer graphics, carries behind it many more techniques than just I look at the floor and I make it look like a carpet instead of making it look monochromatic. Texture will be a trick that will lead to many other tricks, like making displacement map, like taking a picture from the sun, a picture quote from the sun, that will give us just a distance to each object, and then using these pictures from the sun, I'll do a little trick that will tell me for other objects you are exposed to the sun or you're not exposed, helping me building very fast the shadow, not the shading, the shadow of other objects, because I'll know very quickly which one the sun sees versus which one are obscured from the sun. It's other tricks of, again, texture mapping that we'll use later in the course. Cool, thank you. So we didn't get to specular shading, so homework 2 is just diffuse shading and the sketch.
Did you say that was posted or not yet?
Sorry?
Did you say that was out or not yet?
It's out.
Not yet. Will be.
Where is it?
It's
Oh, homework 2 or these slides?
Yeah, these are two. Homework 2 will be out today. It's
Okay.
similar to last year, except that it including specular. It includes diffuse shading. I waited later last year. Yeah. Bye. Thanks.